Here it is, Free Range Digital Design Foundation Modeling. This is Chapter 8. This is the first chapter where we get into iterative modular design, which is second design approach, essentially designing a ripple carry adder, which is made up of full adders and half adders, and a bunch of other material in between here. So this is iterative modular design. The first thing we did was brute force design, and it was extremely limited because it was based on creating a table. The number of rows in the table was determined by the number of inputs. It's exponential relationship. 2 to the number of inputs decided the number of rows in the table. So what we'll see is iterative modular design is also limited, but it works really good for a few modules, particularly the ripple carry adder. So ripple carry adder is our first foundation module. Recall that our foundation modules are these modules, one of 8 or 9 modules that we can build any digital circuit with. The idea here for a ripple carry adder is can iteratively place some modules in such a way as to create a ripple carry adder. And so the modules that we're going to place are half adders and full adders, which we'll design in just a second here. The issue with a half adder is that it is a 1-bit adder, meaning that it adds 2 single-bit values. When you're adding 2 single bits, you have 4 possible cases. The 4 cases include you may have not seen this before. It's important. It's really, in theory, the same as decimal addition, where you add things by columns. The columns may generate some carry values into the next column to the left, which is the more heavily weighted column. For this, 0 plus 0 is of course going to be 0. 1 plus 0 is 1. 1 plus 0 is 1. But 1 plus 1 is going to be 0. And there's going to be a carry. 0, 1 plus 1. Remember, this is binary. 1 plus 1 is 2. There's no such thing as a 2 in binary. It's the same thing as adding 1 plus 9 in decimal. You generate a carry. So when I hit 2 here, I generate a carry. So 1 plus 1 is 0 with a carry. Now we're going to utilize this in a half adder. Remember, this is typical binary addition. For the half adder, first thing we need to do is define what it is. It's a 1-bit adder. It adds 2 1-bit values, typically we call that A and B, and it outputs both a sum and a carry out. And so let's we're going to design this from scratch here. BBD, half adder BBD. This is a sum, and I'll say carry out just for shorthand notation. Inputs are going to be A and B, and that's my top level black box diagram. So it has 2 inputs, so we're going to brute force design this thing. This is A and B. It's going to have 2 outputs, which is a sum and a carry out. So 0 plus 0 is 0 with no carry. 0 plus 1 is 1, no carry. 1 plus 0 is 1, no carry. 1 plus 1 is 0 with a carry. Okay, so this is the truth table. Once again, we got another model of this half adder. So lastly, we want to generate some equations for this. And those are the equations. Last thing we need to do for this is draw a circuit. This is not going to be too complicated, so we can draw this. I see 2 AND gates there that are ORed together for the sum. So we'll see A. There's the lower level circuit for this half adder. Notice that this is the lower level. This goes inside of that box. So that's our half adder. So the problem with a half adder is that it's limited in that even though it has a carry out in the output, there's nothing to do with the carry out. So we're moving towards a full adder, which has the same outputs as a half adder, which is a sum and a carry out, but it also has an extra input, which is the carry in. So overall, the operation performed by a full adder is A plus B plus the carry in. So this is still a 1-bit adder, but it's essentially adding 3 1-bit values. So what we want to do now is design our full adder. And so once again, full adder is very similar to half adder. Exactly the same output, sum and a carry out, but a full adder now has an extra input, which is the carry in. We'll first indicate that, the diagram. And that's our black box diagram. What we want to do next is brute force design. We're going to generate a table for this. So we'll go, this is our table. We'll leave C and we'll consider that a CN so we don't have to write so much information. What we want to do is fill out a sum and a carry out for each of these row positions. So 0 plus 0 plus 0 is 0, no carry. 0 plus 1 is 1, no carry, 1, no carry, and this is the sum is 0 with a carry. Continue on here, we got 1, no carry, we got a 0 with a carry, a 0 with a carry, and last we have a 1, sum of 1 and a carry of 1. And so this is our truth table describing our circuit. Once again, it's brute force design. Next thing we want to do here is write equations for the sum and the carryout. So if looking at the sum, we see that there's 4 1s there, so we'll really quickly jot that out. And same with the carryout, there's 4 1s in the carryout. We'll very quickly write those terms out and then we'll go back and adjust them. So here we go, we have a 1 in this 1 position, so this A and B are zeros, so we're going to represent that with over bars. And here A and C are zeros. Here we have B and C are zeros. And lastly, we have nothing as zeros. For the carryout, we've got this row here, A is a 0. Then we got B is a 0. Then we got C is a 0. And then we have none of the terms complemented. So these are our 2 equations describing that. And at this point, it'd be very easy to write a circuit for this, but we're not going to do that. It's just way too much trouble. But the thing to notice about the circuit is you look at this, and if someone asks you how many AND gates are required for this thing, you just look at this and say 8. Well, if you had to actually implement this, you can see there's one case here where for this row here, both the sum and the carryout could use the same product term, and so they could share the AND gate. In the end, I only need 7 AND gates to implement this particular function. Once again, it is going to look like 4 ANDs feeding into an OR. It is an AND OR type function. I just once again, I just don't want to write all that out. And with that, we will certainly call this done.